So today we are going to look at how are there ways to combine random variables so that we're not having to interpret and manipulate every single piece of data. So let's kind of look at how that works to begin with. So our first example has let x and y be two independent random variables with the following probability distributions. Remember from our last lesson, we talked about how a probability distribution is the list of outcomes and their probabilities. All of the probabilities should add up to 1, and each individual probability should be between 0 and 1 in order to be a legitimate probability model. So they ask us if we let S equal X plus Y. So I'm combining these two sets of data together. We want to create a probability distribution for that combination. So what we have to do is we have to go through and combine each individual piece of data. So I'm going to combine 5 with 1, 5 with 2, 5 with 3, 10 with 1, 10 with 2, 10 with 3. So I went ahead and organized it in a table. So I have my S and I have my probability of S. Remember, anytime we are describing a set of random variables, we usually use a capital letter. And this one they told us is going to be S, not to be confused with sample space. So for my first one, I went ahead and added 1 plus 5, which gave me 6. And in order to get the probability, I just multiplied those probabilities together because two events are occurring at the same time, which gives me 0.12. And this table here, you don't have to necessarily write down. I am going to kind of walk you through each one individually, but we are going to organize it in this table down below. So I did the same thing for 2, I did the same thing for 3, took their probabilities, multiplied them together. I got zero point 0.08 and 0.20. And then I did the same thing for y value of 10. I did 1 plus 10, 2 plus 10, 3 plus 10. So I did their multiplication because two events occurring at the same time. I got 0.18, 0.12, and 0.30. So what I do is I take all of the values of the outcomes. So my 6, 7, 8, 11, 12, 13, and I'm going to place those in the top row of my table, my probability distribution table. And then I took the outcomes 0.12, 0.8, 0.20, 0.18, 0.12, and 0.30 and put them in the bottom row. The only incredibly important thing is that you keep the data together. So 6 is going with 0.12, 7 is going with 0.8. Cannot mix and match here. It has to match accordingly. So I have my probability distribution. Now what we're going to do is they want us to find the expected value of S in our calculator. So I'm only going to do one of these with you because we kind of got some practice on this in the last lesson. So if you still want to go over the steps, we can afterwards, but I'm going to walk you through one finding. So I'm going to go to L1. I'm going to type in my data. So I'm going to type in my outcomes into L1. So 6, 7, 8, 11, 12, and 13. And then I'm going to type my probabilities in the same order into L2. It is very important. I know this is something that came up on practice that if you're not changing L1 and L2 in one var stats, you need to make sure your outcomes are in L1, your probabilities are in L2. If you switch it up and you tell them the probabilities are somewhere else, that's okay, but otherwise you're going to get an error or it's going to give you an incorrect mean or standard deviation. So just double checking my data really quick. Now I'm going to go to stat, over to calc, to one var stats, and I want to have a list of L1 and a frequency list of L2. So I'm going to go to second, number 2, and I'm going to calculate. and then I get my expected value. These two should match. That's usually generally a giveaway that something's wrong in your data if the calculated mean and the sum mean are not the same. They should be the same for this type of problem, and my standard deviation is 2.6. So I'm going to go ahead and fill that in. I have 10.2 and 2.6. So the remainder of the expected values and stuff like that, I'm just going to kind of give to you so we can save some time of not having to re-enter a bunch of different sets of data. So I did the same thing for X. I entered 1, 2, 3 in my L1, 0.3, 0.2, 0.5 into my L2, and I got 2.2 and 0.8718. Did the same thing for Y. 5 and 10 were in L1, zero point 0.4 and 0.6 were in L2. Ran one of our stats, and I got 8 and 2.4495. Now, the thing that we are noticing here is we can use a shortcut for combining random variables in terms of identifying mean and identifying standard deviation. If I am looking at my two formulas here, we're going to see if our rules work for them. So I have a rule for when it's subtraction and a rule for when it's addition. If I am adding two data sets, and something that is very, very important and something that you have to verify prior to being able to do this is that you have independent random variables, meaning they have no effect on each other. One is not changing because the other did something. They are just separate sets of data entirely. So, with that being checked, you can go in and say, if I'm adding x plus y, all I have to do is add the means e to the x plus e to the y. So, if I wanted to get s, which was x plus y, I add 8, I add 2.2, which worked out. Let's see somewhere here. It worked out. There we go. X plus y, we did 2.2 plus 8, gave us 10.2. So that one checks out. It works. Now, the subtraction one works exactly the same. If I were to subtract instead, all I would do was subtract the two expected values from each other. Standard deviation is a little bit different, again, because we are working in terms of variance and things like that. We have to consider that, which is why we have a square root there and we have our variance working. The big thing with standard deviations, you cannot decrease the variability in a data set by adding two sets together. If I am adding two sets together, overall, I'm going to always be increasing the variability. I'm increasing how different these values are from each other because I started with one set, I added more to it. That only increases and changes it. So, something you have to be careful of is for standard deviation, no matter if you are adding or subtracting, we're always going to add our two variances together. So, this is really the same formula for both instances. So I'm going to verify that it works on my data above. I have my standard deviation for group X, standard deviation for data set Y. I took the squared of both of them because that's the variance. And then I take the square root of everything. And that gives me approximately 2.6, which also checks out to be a match to our standard deviation for the combined data set. So this is nice because if you are asked to combine two random variables and you have to get the mean and standard deviation of it, you don't have to go through, which I'm going to scroll up really quick, this whole lengthy process of combining every single data set and then getting the expected value and standard deviation. Instead, you could just enter the data that you have, get your standard deviation and mean for one and the other, combine those two together. Kind of just depends on what workload you're interested in, really. Some people like to just list out the combined data set. Sometimes the data is a little bigger than what we have now, which kind of gets lengthy in time. Again, you don't want to spend too much time on one problem. Going to give you about a minute or so to finish copying this down, and then we will move on to the next page. So these were examples of combining entire data sets together or subtracting them from each other. We also have the instance where we change a data set by applying some type of transformation to it. So, next example, we have the head folks at Google. They decide to brilliantly, though it's not so brilliant, try a random salary assignment for their workers this year. They have the following probability distribution where X is going to represent the salary amount in dollars. So they are paying people 50,000, 60,000, 70,000, and $80,000. And the probability of getting each salary is zero point 0.2, zero point 0.3, zero point 0.4, and zero point 0.1. So first thing we're going to do is get the expected salary and standard deviation of this data set. So again, I'm putting all of this data into L1, all of this probabilities into L2, running one bar stats, and that's going to give me 64,000 and 9,165 approximately dollars just as our baseline. So beyond that, they are going to go in and they are going to give everybody a $500 bonus. So they're increasing the salary amount by $500. So they want us to create a new probability distribution and find the expected value and standard deviation for that group. So I have my additional $500 that I'm going to add on to everybody's salary. I just called it X plus 500. You could also give it a new variable, y. For instance, you could say y equals X plus 500, but you can just state the addition. And the probability distribution does not change. We're still going to have 0.2 in this group, 0.3, 0.4, and 0.1. I'm going to go ahead and run this in my calculator. Again, quickest way to do this. You don't want to have to deal with the formula, especially for standard deviation. Takes a long time. So I got 64,500 and 9,165.15. So what we look at now is how did our expected value and our standard deviation change? I noticed that my standard deviation went up by 500. I noticed my standard deviation, I mean, my mean, sorry, went up by 500, and my standard deviation did not change. So the mean increased, standard deviation did not change. It's going to be kind of important in our rule in just 1 second. Now, after that, they decided, you know what? We're just going to pay you cash. We're going to pay you cash at the end of the year for the salary, and then you manage your money for the entire year, which is not a great plan. So they're going to give out $100 bills, and they're going to say, this time let X be the number of $100 bills they're going to give out. So what we'll have to do, we're creating a new probability distribution based on this bonus, and we're going to find the expected value and standard deviation. If I want to know how many $100 bills they're giving out, I need to take my salary amount and I need to divide it by 100. And that's going to tell me how many $100 bills I need. So I did that. So I got X is going to be equal to 505, 605, 705, 805. Again, the probabilities do not change. They're still going to have 20% getting salary group 1, 30% getting group 2. I ran this in my calculator. I got 645 for my expected value and 91.6515 for my standard deviation. Now, what I'm noticing with this data compared to my original data, which was 64,500 and 9,165, is we have both the mean and the standard deviation were divided by 100, like our random variable was. So when I did just an addition, just an added value to each outcome for my random variable, the only thing that changed was the mean. The mean increased by the same value. When I had a multiplication, technically division is multiplication times 1 over 100, or division, if that's what you want to think of it as, both the mean and the standard deviation changed. And that rule applies across the board. So our formula for this is, if I have an addition, so like an increase or a decrease, it could also be subtraction, it's going to apply to both the, well, only the, sorry, expected value. But if I have some type of multiplication, so some type of value that's being multiplied on or divided by, it's going to affect both the expected value and the standard deviation. So, big takeaway here is adding and subtracting will only affect the expected value. Oops. And multiplying or dividing will affect both expected value and standard deviation of x. Let's fix up my E. And that's because when you're adding or subtracting something to every single piece of your data or every single outcome that you could possibly have, you are increasing everything by the same amount, meaning you have not changed the distances between each value. They stay the same, which is why standard deviation stays the same. When you're multiplying by the same value, but you get different distances between each data set or data point. So standard deviation alters with that. Okay, last page. I know a 3-pager, very rare for us. We are going to go ahead and just tackle some examples together, and then you'll have some time to work on your practice. For example 3, depending on the attendance of a minor league baseball team, the number of hot dogs and sodas is given by the following table. I'm going to go ahead and run both of these for you. I have my expected value for hot dogs sold and my expected value for sodas, along with their standard deviations. If the profit on a hot dog is $1.50 and the profit on a soda is 75 cents, find the average profit on hot dogs and sodas. So, and we're going to be adding something together per game. What is the standard deviation of this profit? So I know hot dogs are costing $1.50, soda is costing 75 cents. So I have to take this into consideration in calculating my profit. So we are going to call the expected value of the profit 1.5 times the hot dogs plus, there's my adding because we're combining both of these items together, 0.75 times my sodas. So all I have to do is take 1.5 times the expected value of hot dogs plus 0.75 times the expected value of sodas. That's going to give me 1.5 times 1,025 plus 0.75 times 680, which is $2,047.50. So in the long run, we would expect them to profit $2,047 on a random game night, randomly selected game night. Now for standard deviation, all I'm going to do is follow our formula, which says I need to take the square root of, so this is kind of combining both, this problem combines both the linear transformation and the combining random variables together. I'm going to multiply since this is going to multiplication affects standard deviation. 1.5 times our standard deviation of hot dogs squared plus 0.75 times standard deviation of sodas squared. Plug that into my calculator, and that gives me a standard deviation of $1,241.92. Now remember, for standard deviation, you are using the same formula no matter whether you are adding data sets together or you are subtracting data sets from each other. Going to give you a little bit of time. I will say the hardest thing that I've seen students encounter with this topic before is just remembering the fact that addition only affects expected value, multiplication affects both. That's the hardest thing to differentiate between. Beyond that, it is just looking at the formulas and being able to use them appropriately and remembering how to do expected value in your calculator. So let's go ahead and look at our last couple of examples. We have two Pro Bowlers, Larry and Sam. They have the distribution of scores shown below. We have their mean, we have their standard deviations, and they want us to find a couple of different scenarios. So I have the expected value of Larry plus Sam. So all that is the expected value of Larry plus the expected value of Sam, which is 209 plus 221. My answer is 430. Then they want us, mu is the same thing as expected value, don't forget. Find the expected value of Sam minus Larry. So I'm going to do mu of S minus mu of L. I just do 221 minus 209. That gives me 12. Remember, mu of x is the same thing as E of x, mean expected value. Though generally they ask you more for expected value than they do the mean. For my standard deviation, they want us to find of Larry plus Sam. So I'm going to do square root of Larry's standard deviation squared plus plus standard deviation of Sam squared. Going to plug in my values. That gives me 26.0768. And before we kind of jump to the other side, I do want to look at E, because this is asking me for standard deviation of Larry minus Sam. Well, remember we talked about how the standard deviation formula does not change because we cannot decrease your variability. So this is actually the same answer. 26.0768. You can just say same as above if you'd like. But even though they are, one is addition, one is subtraction, standard deviation cannot decrease. We will never subtract standard deviations from each other. We will always add. Now for D, we just want to take the standard deviation and we want to multiply it by 3. Well, because multiplying affects standard deviation, I'm going to just take that value I multiplied by and multiply it, which is going to give me 42. Something that I want to include that I don't have here necessarily is if I had standard deviation of Larry and I was increasing it by 10, for instance, and I asked you, what's the value here? Because of the fact that we do not change standard deviation when we're increasing values. So that data set did not increase. The standard deviation of Larry would still just be 14. Does not change from addition and subtraction. Will stay the same. It does change when you multiply. That's why this multiplied to be 42 will not change for addition or subtraction. And then we we are increasing our data set by 4 plus 3L. So because both addition and multiplication affect your expected value, we're just going to apply both of these transformations to Larry's average, and that's going to give us 631. So what will happen is you do have a practice assignment for this on Pearson. I also am opening up a quiz for 4.4 and 4.5 this afternoon.